Hello, and welcome to another exciting episode of Limits. We're going to be covering section 2.3 today, which is calculating limits using limit laws. So up to this point, we had been finding limits either by looking at a graph or a table. And really we'd been estimating. We hadn't been finding exact answers. So in this section, we're going to learn about some laws that help us find exact answers to answer limit questions. So this is the Desmos activity. So you are assumed to know the usual stuff as far as reading a piecewise function. We've seen limit notation already. Recall that the constant function is just a horizontal line through the value of c on the y-axis. The identity function is the name for the function y equals x or f of x equals x. Remember how transformations affect the graph of a function, and remember rational functions and wholes. So we're going to start off by looking at 5 basic limit laws, and we're going to use these to help us break down more complicated functions and find limits of the smaller parts. So these limit laws are in your textbook in section 2.3. So if I go to the e-text, here's the box with the limit laws. So I just want to go through these and show some examples. So the first law is telling us that if we have the limit of the sum of two functions, we can find that by finding the limit of each function and adding them. And the same goes with subtraction. So let's look at this function. Here's an example. Another way to word this law is the limit of the sum is the sum of the limits, or vice versa. It applies with difference too. So looking at this, the limit of this function as x approaches 1 of x squared plus the quantity x squared minus 1 over x minus 1. So this law is telling me that I can break this up into two limits, the sum of two limits. The limit as x approaches 1 of x squared, and the limit as x approaches 1 of x squared minus 1 over x minus 1. And so I can apply that law that used the terminology f of x and g of x. I'm saying, okay, let's call g of x that first term and f of x that second term. I can find the limit of each function. So I still need to use a graph to do that at this point. So here's g of x equals x squared. And the limit as x approaches 1, if I follow along the graph as x approaches 1 from both sides, right and left, I see that the limit is 1. And then my other function, this rational function, the limit as x approaches 1, I have a hole at x equals 1, but that's okay. The limit is still 2. So therefore, I can just add these individual limits, and my answer is 3. And we can verify that graphically. So this dashed graph is the actual graph of the sum of those two functions. And if you remember how to add functions graphically, you remember all you're doing is adding the y-coordinates of points on functions for a specific x-coordinate. That's how you get the graph of the sum. So that's all that's happening here. So now the next law, we had the sum, we had the difference, now it's multiplying by a constant. This next law tells you that you can take the constant, pull it out of the limit. So you can just find the limit of a simpler function and then multiply it by that constant. So if we look at g of x equals 3x squared, what this law is telling us is if we take the limit as x approaches 1 of this function, we can just pull that 3 out and look at the limit of the simpler function as x approaches 1 of x squared? Well, like we saw from the previous slide, the limit as x approaches 1 of x squared is just 1. So this law is telling us that we can just multiply 1 by that constant c, and our limit is 3. And it makes sense that, when you multiply a function by a constant, if you recall from pre-calculus, you are doing a vertical stretch. So as your x-coordinates are approaching 1, the y-coordinate is just 3 times the y-coordinate of the function f of x equals x squared. So it makes sense that the limit is just 3 times the limit as x approaches 1 of x squared. The next law is the product law. So that's telling us the limit of the product is the product of the limits. And if we look at this example, we can see how this would come in handy, because you don't really want to have to multiply this out. So let's look at the limit as x approaches 1 of this function. This law tells us that we can look at the limit of each of these factors and then multiply those limits. So if f of x is this first factor, x to the 4th plus x plus 1, and we call g of x the second factor, x to the 5th plus x squared, I'm just taking that, I'm finding the limit of each factor. And again, we're going to need to look at the graph to see what these individual limits are. So this is x to the 4th plus x plus 1. This function is g of x, is x to the 5th plus x squared. And if you look at the individual limits, you see as x approaches 1 for g of x, the limit is 2. As x approaches 1 for f of x, the limit is 3. Therefore, the limit of the product is just the product of those two limits, or 6. And we can verify that by actually graphing the product function. So it's this dashed graph. I can see that as x approaches 1 on the product function, the limit is 6. And you can look at it numerically too. The next one is the quotient law. So the limit of the quotient is the quotient of the limits as long as the limit of the denominator is not 0. So again, let's look at this example. The limit as x approaches 1 of ln of x plus 1 over e to the x. Well, this law tells me that I can find this limit by looking at the limit of the numerator and denominator separately, right, and then performing the division. So I can use this here because e to the x, recall, is never 0. So it's not a problem to use the quotient law here. So again, I need to look at the graph to find these limits. So if we look first at the numerator, ln of x plus 1, that's this graph. And I can see as x approaches 1, that graph approaches y value of 1 as well. And the limit as x approaches 1 of e to the x is 2 point something. It turns out it's 2.7-ish, or 2.718, which is an approximation of e to the first. So therefore our limit is 1 over about 2.7, which is about 0.368. Here we feel a little bit better verifying it graphically and numerically, because e is not kind of a natural thing that we're used to working with every day. So this dashed graph is the quotient, and you can see that as x approaches 1 from the left and right, the y value is 0.368, and you can see it numerically here too. Okay, so that's good to know, but notice that in these problems, we still looked at the graph to figure out what these individual limits were when we broke it down into products of limits or sums of limits. So this next group of laws is going to help us actually find those individual limits that we couldn't figure out unless we looked at the graph. So I'm just listed up the next 6 laws here. So that first one is the power law, and this tells us that if we have a function raised to an integer power and we're taking the limit of that, we can actually find the limit, bring the limit inside the exponent. So we can evaluate the limit of just f of x and then raise that limit to the nth power. And this is derived by repeatedly applying the product law. So you can look at the product law we saw before, and f of x to the n is f of x times f of x to the n minus 1. So you apply the product law there, and you just keep doing that repeatedly. F of x to the n minus 1 is f of x times f of x to the n minus 2, etc. So this is just basically telling you that you can pull the limit symbol within the exponent. So let's look at an example. So here we have the limit as x approaches 2 of quantity x plus 1 to the 4th. So that law is telling me that I can bring this limit symbol inside this power, right? So I have this. So I can find the limit of this expression inside this power. So I can apply the sum law that we just saw. So what's inside here is equal to the limit as x approaches 2 of x plus the limit as x approaches 2 of 1. But now we're going to look at 2 other laws that will help us definitively say what these are. So looking at graphs, we've kind of pretty intuitively figured out what they are, but this law is going to firm it up for us. So we're going to look at 2 more laws before we answer this, and we'll be back to this problem in a minute. So the first one we need to look at involves the limit of the constant function. So I'm going to flip back to my last problem. Notice that I have the limit as x approaches 2 of 1. 1 is just the constant function, right? So that's what we're going to use. This law is what we're going to use to help find that. So the limit of a constant function is just that constant, which makes sense because the y value is never changing for a constant function. It's always the same. It doesn't really matter what the x value is. The y value, in this case, when the f of x equals 4, it doesn't matter what x is. Y is always 4. So that makes sense that the limit of a constant function is just that constant function. So I'm changing my horizontal line here, and it doesn't matter what my x value is, right? The y value is always the same. So that tells me that the limit is always just c, the constant. The next law is going to help us figure out the first part of this problem. So the limit as x approaches 2 of x. Remember that y equals x is called the identity line.